Multigraph just means if you look at certain pairs of vertices, you'll notice that there are extra edges. In other words, between these two vertices, there are two edges. We don't need both of them. We only need one bridge to cross from one vertice to the other. So there's extra edges. It's called a multigraph. Now Euler's idea was that if we want to find the path in this circuit, we use some of the same strategies that we have for other normal graphs, which is, well, find out the degrees of the vertices, and in this case, the degree of this vertex is 3, and that's 5. So we know the start and end at one of these vertices, but he extends it to say, okay, let's turn this multigraph into a regular graph. Let's take out the pairs of edges that we don't need, that form the multigraph, and then put them in later. So the two edges here that go between the vertices, they're extra. We don't need both of them. So Euler said take them both out, take a pair out. And why? Well, in this vertice, the degree was even. It was 1, 2, 3, 4. In this vertice, the degree was 1, 2, 3, 4, 5, 6. It was also even. Now, in graph theory, especially in situations where we want to draw a graph with a single line, whether a vertex is even or odd is very important. So by taking two edges out, this even vertice remains even, and this even vertice remains even, right? Because if you start with an even amount, right, let's say you have 6 or 8, and you take 2 away, a pair away, you still get an even number. And also, Euler's theorem idea works, sorry, not his theorem, his idea works for odds. If we had odd degree vertices, what happens to an odd number when you take a pair out, like 5? 5 minus 2 is 3. 7 minus 2 is 5. 11 minus 2 is 9. So in other words, take 2 away from an odd degree vertex and you still have an odd degree vertex. So by taking pairs of edges out, we preserve the type of degree for each of our vertices. All of our even vertices remain even. All of our odd degree vertices remain odd. And why is this important? Oh, that's my dog. So why is that important? Well, remember that if we took just one edge out, this vertice would have an odd degree. So it would change from even to odd, and this would change from even to odd, and that's a problem. Because then we would have two more vertices that are an odd degree, which means we couldn't find the path of circuit. And that's something we talk about in other videos, right? We don't want to mess with the number of odd degree vertices in our graph. So we take these two out. The next pair of extra edges I have is right here. So I take these 1, 2 edges out. And that means that this 1, 2, 3, 4, 5, 6 degree vertex becomes a 4 degree, still even. And this 1, 2, 3, 4 degree vertex becomes a 2nd degree vertex. And now another set is right here. We don't need 2 edges there, so take those out. So now this becomes not a 5th degree vertex, but a 3rd degree vertex. So I'm going to fix that. Oops, wrong color. 3rd degree vertex. Oops, that's not the right pen. And this becomes a 2nd degree vertex. So now we keep going. Are there other redundant edges? And I do see at least one more. It's right here. Right, we don't need these 2 edges, so take that pair out. So this is now a 2nd degree vertex, and that's a 2nd degree vertex. And I think we've accomplished our goal initially, which is to take out all the pairs of edges that actually make this a multigraph. So this is no longer a multigraph. This yellowish graph is now a normal graph. So what do? Well, our onion skin algorithm is quite useful here. We know we have a path, so we draw a path from one of the vertexes to the other. So I'm going to draw right from this one to this one, and we start finding our path, right? So now that would be a path. We want to include every edge. So we also want to include, if I start here, go along. Well, I missed some, right? I missed these, and I'm going to keep going, right? And now I'm going to try and form a circuit, get back to this point, and I keep going, Okay, oops, we'll go this way actually, include these points, come around, keep going, and I get back to this point here. So what does that mean? Let me actually change the original path so we can see the progression here. So originally we had that red path, and we're trying to find the path in this graph. So we just go down and over here, but we didn't include all these other edges. So now we go down, and then we include this purple path, right? Come back to this vertex and then finish. But we still haven't included these edges, so we want to include them as well. So we start here, and instead of going down here, we want to include these edges. So to do that, I just travel on them, on this green circuit right here. So now, the way to solve this normal looking graph, we start by walking along the green edges. Then, we walk down this one red edge and take the purple route all the way around, and then finish on the red route. So that would be the solution for this graph if it were normal. But what about all these points where we had the extra edges? Right, we had a vertex here and here and so forth. What do we do? Well, Euler's idea was that, well, you already solved the puzzle, so why not just walk that route and then incorporate the pairs of edges as you go along? So this might be what it looks like. Let's use purple. So we start here at 3, at this vertex. We walk our green route. Sorry, this should not be orange. We walk our route, and we encounter our first point where we had a multigraph. But no problem, because all we have to do is walk across one of the edges we took out and then walk back. And now we're here. And now we continue our path, so we can solve the multigraph. We walk here, and we forgot these two edges, no problem, right? We just cross one, and then come back. And then we keep going. Well, our original path was to walk back to the starting point, down the red, and then proceed on the purple path. This is already taken care of, right? Keep going, and oh, we encounter another pair of edges that we left out before. So what do? Well, cross one, hit this vertex, come back, and then continue along the purple path as we originally designed. So we keep going, keep going, keep going. Oops, and actually let me go back. And I don't have to do it right now, but I can. I want to incorporate these two edges, right? So I travel along one, and then come back, and then finish the purple route, and then climb up this red route right here, and notice we've crossed the entire graph. And that did seem like an exhausting process. I just want to take my time in explaining it, but it really is quite easy to do, where you take out the pairs of extra edges and then solve your path, or your circuit, depending on what's happening, and then add those edges back in. And we'll look at another graph, and then we'll kind of reverse this. So what if you started with a solution? How could you extend a solution to any multigraph? All right, hope